Okay, I'm going to review the exam number 2 solution. And I know you don't have your exams in front of you, and you may not even remember if you have Form A or B, but of course I want to review the concepts. So problem 1 is a probability distribution, and it's defined by this table here. So to find the mean and standard deviation, you really just want to put this in the TI. Remember, we can find the mean manually. The standard deviation, we need the technology. So, right? Use your L1, L2 lists, put the information in, run that one variable stats procedure. So for Form A, you get 3.93 for mean and 2.36 for standard deviation. Now, what's the probability the realtor sells 4 or more homes in a single month? Well, that's probably X greater than or equal to 4. And all we really want to do is just add these 4 individual probabilities here, and you'll get 0.54. And then, is it unusual for a realtor to sell no homes in a single month? Well, the probability of X equals 0 is 0.12, and that is not less than our threshold of 0.05. All right, so it would not be considered unusual. On Form B, of course, the numbers are changed just a little bit. So now your mean and standard deviation are 3.58 and 2.03 respectively. And now what's the probability the realtor sells 3 or more homes in a single month? That's X greater than or equal to 3. So we want to add these probabilities of 3, 4, 5, 6, and 7. You'll get 0.61. And then, is it unusual for a realtor to sell no homes in a single month? Well, in this case, the probability X equals 0 is 0.01. That is less than 0.05, so that would be considered unusual. Now, stay with Form B, right? Problem 2, a binomial distribution problem. All right, this is really a quality control problem. So they randomly select and test 25 components, except the whole batch if there are fewer than 2 defectives. So with the binomial problem, I identify N and P. N is 25, and P, the probability of having a defect, is 0.04. So fewer than 2 is X less than 2, but that is the same as X less than or equal to 1. So I can use the binomial CDF function, remember, because we have this specific mathematical relationship. That's 0.736. You could add the individual probabilities of 0 and 1 if you wanted to and get the same answer. On Form A, again, very similar. Now we test 29 components. N is 29. Probability defective is 0.06. And now we want fewer than 3 defectives. That's X less than 3. But that's the same as X less than or equal to 2. Again, in that case, I can use binomial CDF directly and get 0.749. Okay, moving on to problem 3. Again, this is Form A. Again, another binomial distribution problem. So here, net recognition rate of a certain coffee shop chain is 60%, and we randomly select 9 Kauffelton residents. All right, N is 9, P is 0.60 here. Sorry, that's a little typo. All right, so probability exactly 6 of the 9 residents recognize the brand name. That's one individual probability. We can use binomial PDF. You get 0.251. The probability all 9 residents recognize the brand name. Again, that's one exact probability, X equals 9. Again, I can use binomial PDF, and that would be 0.01. Now, the probability at least 7 of the residents recognize the brand name. Okay, at least 7 is X greater than or equal to 7. So that's the probability of 7, 8, and 9 all added together. So you can calculate the 3 individual probabilities and add them up. But using our logic, X greater than or equal to 7 is the same as 1 of probability X less than or equal to 6. And there I can use binomial CDF. And there you'll see 1 minus 0.768 is 0.232. These probabilities here are essentially identical. And is that unusual? Well, 0.232, again, that is not less than or equal to 0.05, so it is not considered unusual. On Form B, again, the numbers will just change slightly. All right, so now recognition rate is 52%. There's our P, and now we randomly select 10 residents. N is 10. So probability of exactly 8 of the 10 residents recognize the brand name. That's one exact probability. Use binomial PDF, 0.055. Probability all the residents recognize the brand name. That's X equals 10. Again, just use binomial PDF. That's 0.001. And then here, find the probability at least 8 of the 10 recognize the brand name. Again, as I said before, you can calculate the individual probabilities for 8, 9, and 10 and add them up, get 0.069. But, oops, here's another little typo, X greater than or equal to 8. That's the same as 1 minus probability of X less than or equal to 7. and you can use binomial CDF there, and you will get 0.070, but again, these probabilities are essentially identical. And is this unusual? Well, 0.070, again, not less than or equal to 0.05, so it is not considered unusual. All right, I'll continue to stay with Form B here for problem 4, then I'll jump back to Form A. So this is really a binomial distribution problem in a way. So we have determined 72% of consumers have heard of Dell Computer Company, and they surveyed 900 randomly selected consumers. So we'll know N is 900, P is 0.72, and Q is 1 minus P. So in this case, it'll be 0.28. So use the range rule of thumb to determine the minimum, maximum usual values, or significantly low, significantly high. All right, so what we need to do is calculate these values mu plus or minus 2 sigma. So mu is N times P, which will be 648. And sigma, this is the formula I gave you on the formula sheet, square root of NPQ, that'll be 13.5. So when we calculate the mean plus or minus 2 sigma, all right, what we'll get is a lower value or minimum usual value of 621, maximum value usual value of 675. If a value is in between those boundary values, it's not considered unusual. Outside those two values, it would be considered unusual. So in groups of 900, would 684 be unusual? It would be, right? 684 is larger than this maximum usual value of 675. That would be considered unusual. Going back to Form A, all right, now N is 800, and the recognition rate is 82%, so P is 0.82, Q is 0.18. So again, we have to calculate mu plus or minus 2 sigma. So mu is NP, and so this is 656. We use the formula to calculate the standard deviation. That's approximately 10.9. So now our minimum usual value is 634, maximum usual value 678. So part B, for groups of 800, would it be unusual to get 657 consumers? Well, now notice 657 is within the maximum and minimum usual values, so it is not considered unusual. All right, next page of the test is when we start to work with our normal distribution. So volume of sodas and quart soda bottles are normally distributed at the mean of 32.3 ounces, standard deviation of 1.2. So there's your mean mu and standard deviation sigma. What's the probability the volume in a randomly selected bottle will be more than 32 ounces? So that's probability of X greater than 32. And I've always said draw a picture, right? So the distribution is centered here at 32.3. 32 would be just a little bit to the left of that. So we know that probability has to be more than half or 0.5. But we'll use normal CDF. Lower bound is 32. Upper bound, 1E99. Put in your mu and sigma. And that probability or area is 0.597. And why don't I show problem 6? Similar problem, right? Bank loan officer rates applicants for credits. All right, there's our mean of 200, standard deviation of 50. And what's the probability of a rating between 175 and 225? So again, I'll draw the picture. And again, this is the probability we're looking for, X in this range of values. So lower bound will be 175, upper bound 225. Put those into normal CDF. There's your mu and sigma. Probability is 0.3829. On Form B, problems will be very similar, but now here I want the probability that the volume of soda would be less than 32. So now X is less than 32. We'll draw the picture. We know this area probability has to be less than half based on the shading. Lower bound is minus 1E99, upper bound 32. Put them into normal CDF. There's your mu and sigma, 0.4013. And then for problem 6, again, here's our credit ratings. What's the probability now a rating would be between 190 and 240? So again, lower bound is 190, upper bound 240. There's your mu and sigma, 0.3674. Now, just as we can be given X values and find a probability with the normal distribution, we can also do this in reverse. We can be given an area or probability and then have to find an X value using the inverse norm function. That's what problem 7 is. So here, mean and standard deviation is the same, but find the 95th percentile, P95, which separates the lower 95% from the top 5%. So what we're looking at is there's some x value for which the probability less than or equal to that would be 0.95. So here's our distribution center to 200, and right, if we shade 95% of the area, there's some x value that 95% of the values would be less than that. And so remember, with inverse norm, the input has to be cumulative area from left to right. Right? So left to right here would be 95% or 0.95. I'll put that into inverse norm, and mu and sigma is 250. And we get 282, which makes sense based on our picture. It should be some value greater than 200. And on Form A, for that problem, here I wanted the 70th percentile. Again, that x value has to be somewhere to the right of 200. This cumulative area from left to right will be 70% or 0.7. So again, I'll put that into inverse norm. There's mu and sigma. This value is 226. And again, that makes sense with our picture. Okay, and we'll look on the bonuses. Okay, so on Form A, all right, a multiple choice test has 8 questions and 4 possible answers. If you're guessing, all right, n is 8 here, and if you're guessing, you have a 1 in 4 chance, or p would be 0.25 of getting a question right. So what's the probability of answering 6 questions correctly? That's one individual probability. We can use binom PDF. That'd be 0.004. On Form B, all right, now the test has 7 questions and 5 possible answers. So your probability of getting one right is 1 out of 5 or 0.2. So probability of getting exactly 5 right would be use binomial PDF. You'll get 0.004. All right, staying with Form B, all right, we have a machine with 7 identical components which function independently. All right, and we have a probability it will fail. That's our P. So N is 7, P is 0.18. The machine will stop working if more than 2 components fail, but find the probability that the machine will continue to work. So the machine will continue to work if 2 or fewer components fail. It only fails if more than 2 fail. So the probability that it continues working is only if 2 or fewer fail. That's x less than 2, and because of that symbol, I can use binomial CDF. There's N and P and 2. That's 0.885. And on Form A, oops. All right, and now the machine will stop working if more than 4 components fail. That means it will continue to work if 4 or fewer fail. So again, that's probability of x less than or equal to 4. N is 12, P is 0.25. Again, we can use binomial CDF, and that probability would be 0.842. All right, and lastly, all right, again, this is sort of a quality control problem, right? Not every part that be manufactured will be manufactured correctly. They all vary a little bit. And so we want weights that would, find the 2 weights that separate the top 2% and bottom 2% for these machine components. So here I want to use inverse norm. So you see we have this lower tail area of 2%, upper tail area of 2%. So to find these boundary values, all right, is sort of the specification limits here. All right, for the lower value, the cumulative area from left to right is 0.02. And then I put in the mean and standard deviation, we get 8.37. But for the upper value, this cumulative area here is 0.98% or 0.98. So then I'll put 0.98 into inverse norm, and then there's the mean and standard deviation. And we get the upper value of 8.57. And then on Form B, again, the numbers change slightly, but the picture looks the same, right? What are these weights that determine acceptance limits, right? So here's our lower 2%, upper 2%. Again, cumulative area from left to right for the lower is 2%. So I'll put that in as 0.02 here. And there's the mean and standard deviation. And then for the upper, it's 0.98. And so I'll put it in there. There's mean and standard deviation. So 8.48 and 8.76 are your limits.